So speaking of broad categories of graph, one that we've sketched most of the time is the simple graph. A simple graph is a graph in which each edge connects two distinct vertices, different vertices, and each pair of vertices is connected by at most one edge. In other words, by no edge, or one, but not more than one. So all of our special types of graph above are simple graphs, as we sketched above. And the thing that the definition does is it says it has no loops, because each edge has to connect two different vertices, not just one vertex to itself. And there are no what we'll call multiple edges. No two vertices are connected by more than one edge. So those are simple graphs, and we've drawn a bunch of those. So let me just draw again one that's not simple. This one is not simple. So let's just take a square to start it off with, and do something like this maybe, and put another edge here like so, and I'll label this A, B, C, D, E. That is not simple because of the multiple edge. Okay, that right there. Another one, just take the triangle here maybe, and I'll put a loop here, and this is A, B, and C, and this means it's not simple. There's a loop, and this up here is called a multiple edge. Multiple edges, really. Multiple edges, there's two of them right there, and when it should be clear what I'm talking about, but I'm talking about those two edges right there that connect A and D. So if in a graph two distinct vertices are connected by more than one edge, those are called multiple edges, just like I was saying. And a loop is an edge in a graph that is incident on only one vertex, like this guy up here. Such a graph, if we need to distinguish it from the simple graph, is called a pseudograph. Okay, so those are just broad categories. Now, another very general important type of graph is a bipartite graph. The bi means two here. So a simple graph, first of all, we'll insist it's simple, so no loops or multiple edges, with a vertex set V and an edge set E, is bipartite if there is a partition of the vertex set into two sets. By partition, I mean that they are disjoint sets whose union, if you put them together, you get the whole thing. So it just splits the original set into two different sets. And the other condition on this, that each edge in G, whatever edges there are, connects a vertex in V1 and a vertex in V2. So more to the point, two vertices in V1 are not connected, and I should say no two vertices in V1 are connected. That might be a little better, right? No two vertices in V1 are connected. No pair in V1, and ditto V2. No vertices, two vertices in V2 are connected. So a bipartite graph might look something like this. Let me give you some examples. So here's one bipartite graph. May not look like it right away, but that's bipartite. Let me label the vertices, A, B, C, D. So V is equal to the set whose elements are A, B, C, D. And what I want to do is come up with what's called the bipartition. Whoops, the bipartition is the actual pair of sets that split the vertex set. So let's come up with a bipartition so that within each of the sets we have no connections, but we do have between the two sets. So let's just look here and talk about this. So if I put, well, let's start with A. If I put A in a set, then that set cannot include B or D. So a natural way for V1 would be to start with A, and that would mean that V2 would have to have B and D. It cannot be in V1. because A cannot be connected to other things in that set in the bipartition. So hopefully that works out. Let's just see. And then what else can be in there with A? Well, C could be in there with A, right? Does that work out? Yeah, because A and C aren't connected. And so that will be the one set. And the other set, let's just check. Does that work out okay? So B is in here. So B cannot be connected to A or cannot be joined up with A and C in the same set. That's okay. But B and D can be in the same set since they're not connected. So in fact, there's a bipartition. This is a bipartite graph. Now, one way to write bipartite graphs, or draw them, I mean, is to put one of the sets up here, V1, so that'd be A and B, A and C, sorry, and the other set down here, V2, and that would be B and D. And draw the graph that way. And if we draw the graph that way, then A is connected to B and D, and C is connected to B and D. And actually that turns out to be all the connections. So that's the same graph. I just drew it a little differently. But now you can see the two sets in the bipartition real clearly. Now another thing that we can do here in investigating whether a set is bipartite is to note what I did up here was I actually marked the vertices that will be in the two sets differently. I use two colors, and in fact that's a perfect way to do it. A graph is bipartite if and only if each vertex can be covered with one of two colors, so that each pair of adjacent vertices have different colors. Adjacent vertices have to have different colors. If you can do it with two colors maximum, then it's bipartite. So here's some examples. Here's G1. G1 consists of 4 vertices. There's 4 vertices and no edges. That's bipartite. Because we can subdivide that into 2 sets. Let me label them first of all. A, B, C, D. And in fact, anyway, you split them up is going to work out, right? So in this case here, for example, we could say, let's see. Let's take A, B, and D in one set. That'll be V1, and this will be V2. Now, isn't it true that every edge in this graph, and there are none, every edge connects something in V1 to V2, but there are none. Alternatively, it's equivalent to say, we've split this into 2 sets, so none of the vertices in V1 are connected to each other, and no two vertices in V2 are connected. So that's a bipartition. As I said, there's, any way you do that, it's going to be a bipartition. So let's take another one. How about, let's take this one here. Is this bipartite, that graph there? This is just a simple K3 or C3, however you want to say it, K3 or C3. It's the complete graph on 3 vertices or the cycle graph on 3 vertices. Is that bipartite or not? Well, let's see. Let's take this one right here and say we color it blue. Then that would mean I'd have to color the other vertex here green, but that would mean that this vertex here can be neither blue nor green if adjacent vertices are going to have different colors. So I'm stuck in this case with using a third color, and this one is not bipartite. Not bipartite. So let's investigate some specific cases. Which cycle graphs are bipartite? C3 is not. But earlier we looked at C4, even though we didn't call it that. This one is bipartite. C4 is. Is C5 bipartite? C5. C5. Let's see. Let's start off with the green. If we do a green here and a red here, whoops, that's not red. And I lost an edge. And a red here, and then a green here, and a red here. Then I'm in a pickle. We're in a pickle here because this last one can neither be green nor red if it's bipartite, or I mean if that's to be a different color. So we'd be stuck with some other color like black here. So that one is not bipartite, and you can probably see how this is working out because as you color the edge or vertices, coloring vertices must alternate as we go from V1 to V2 through Vn in Cn, those being the vertices in, say, clockwise order as we go around there. So these must alternate colors, maybe green, green, whoops, that's a blue, isn't it? Let's try this one here, green, etc. So these alternate. And so if n is even, then it works all the way to the end. So if n is even, this would be green, if n is even, and Vn and V1 would be different colors. If n is even, it is possible to alternate colors. If n is odd, then V1 and Vn minus 1, that's even, have different colors. So Vn must be, I'm running out of room here, I'm going to squeeze it down here, a third color. So what does that say? So the cycle graphs are bipartite only for n even. So C5 is not bipartite. Whereas, C6 would be, and so forth. So I asked another question there, and that is Q3 bipartite? And I think I'll let you think about that, and maybe we'll talk about that one in class. Okay?